All right. So the topic for today is monitoring in Postgres. I'll briefly describe monitoring in Postgres, and then we'll talk about a specific monitoring feature in Postgres that has been recently developed and has been committed in Postgres 18. So let's begin. Agenda. So like I said, I'll touch upon various monitoring systems in Postgres, and followed by that, I will describe the components used in this monitoring feature that I'm going to talk about. I'll describe the details of the monitoring feature, which is memory context statistics monitoring. I will describe the design iterations and then also show you the function signature and the output. Okay, so let's look at what are cumulative statistics. Cumulative statistics allow collecting and reporting of information about Postgres, information like accesses to tables, details about any background process like wall writer. So all of that can be obtained using cumulative statistics. You must have obviously seen the names like PGStat all tables, PGStat wall. These are functions and views that are used to display such statistics. These statistics are collected by a Postgres process locally first, and then they are, whenever a backend is idle, uploaded or rather shared in a shared memory. So that's the way a backend goes about collecting such statistics. These statistics are mainly stored in the shared memory, and the views that you see, the names here, some of these views read these shared memory to get more details about these statistics and display it to the user. These statistics are flushed to disk by a checkpointer just before a server is shutting down, so that when a server starts up again, these statistics are available and you don't have to start from scratch, unless a server has crashed before, in which case these statistics won't be available. Let's look at dynamic statistics. So these are another type of statistics. They're collected very similar to cumulative statistics, but these are more real-time. So as I explained, the cumulative statistics are first collected locally and then shared in the shared memory whenever a backend is idle. But in this case, dynamic statistics are shared instantly in the shared memory whenever a particular event happens. So the examples would be PGStat activity, PGStat progress vacuum. So these statistics report the progress of a command. For instance, vacuum is a utility command, and these types of statistics help report progress of this command. These statistics are controlled by a hook, which is track activities. If this is on, then only a backend will go ahead and share the statistics in the shared memory. So these are the two types of statistics which are used for monitoring. There is, of course, a whole new category of statistics, thank you, which are planner statistics. So these statistics are used by a planner to optimize its functioning. So these are not covered in my presentation, but I would just like to note it here that these two are not the only types of statistics in Postgres. The third one, which is the planner statistics, are a different category. So let's look at basics of the design of a monitoring feature. So first thing I would say you need is a monitoring function that would read statistics from shared memory. This is usually defined in Postgres as a SQL interface function, and which has an underlying C implementation. These functions are also then used in views so that they can provide a better output to the user. Second component is the shared memory structure to store the statistics. So a process that is publishing the stats is different from a process that is querying the stats. So we need a shared memory to coordinate between these. And the shared memory could be a dynamic shared memory or a static shared memory. Currently, monitoring systems in Postgres use both. The third component is PostgreSQL process updating the statistics. So this is a manner in which a Postgres process updates the statistics. Like I described previously, cumulative statistics are updated first locally and then in shared memory. Dynamic statistics are updated directly in shared memory. And there could be another type which I'll describe more in my future slides. These statistics are on-demand statistics. Like a Postgres process will only publish these statistics when there's a demand for these statistics. So this will be covered in the feature that I'm going to describe. Oh, I'm sorry, I just missed another component, which is synchronization between processes. This is obviously, as you would imagine, would contain various locks and signaling mechanisms that would be used to signal between these processes. So let's look at this feature that I was talking about, monitoring of memory context statistics. So let us first understand what memory contexts are. Memory contexts are used to group memory allocations in a Postgres process. A Postgres process groups these allocations so that whenever it wants to give back the memory to the operating system, it can just reset the context. So all these allocations will be freed together. So a backend can create any number of memory contexts at the time of allocating memory. So whenever a backend wants to allocate a memory, it can first go ahead and create a separate context for its allocation. These memory contexts are arranged in a tree-like structure. So if a memory context can be a child of a particular context, and it itself can have a number of children. When a parent context is deleted, space allocated by all the children are also deleted. And at this, since I'm talking about the tree structure, the root of this tree structure is the top memory context. Allocating memory in this context is equivalent to doing a malloc, because otherwise we do palloc when we allocate memory in Postgres. So doing a palloc means allocating memory in a particular context. So yeah, and for reporting purposes, for all these monitoring views, the levels of the context start with 1. So whenever in an output of a PostgreSQL monitoring function, if you see level 1, that means top memory context, and so on. And each memory context contains statistics that keep track of the amount of memory it has allocated, amount of memory that's free. These stats can be used to report the picture of your memory consumption. So, so these statistics are going to be used in the feature that I was talking about to report stats. Why is there a need for memory contexts in 18, monitoring in 18? Because there are a couple of already existing functions which do a pretty good job of describing memory contexts. So the first one is PG backend memory context. What it does is it provides a view of the memory of a local backend. So one thing that's missing here is that it cannot provide memory of any other process except itself. So it is restricted to client backends, and it can't be used for auxiliary processes, wall writer, or any other process in Postgres. PG log backend memory context is another such function, and it appends the memory to logs, but again, one has to go through all the logs and filter the logs to actually get the stats. So there is a scope of improvement here, and that's what the monitoring function is handling. So here I'm describing a bit of implementation detail of that monitoring function. What this monitoring function does is it signals a Postgres process and waits for a response of statistics before giving the statistics back to the user. How you do that in Postgres is you define a C function and provide an SQL interface for it. These are names of some files that are used in implementation of such a function. You have to add an entry for this SQL function in pg_proc.dat, and you have to include the mgr protos.h in the implementation. Wherever you have implemented the C function, there you have to include this file so that you're able to create this function. So now I'll look into some of the infrastructure that is used to create this. And for that, I would like to first describe dynamic shared memory. Dynamic shared memory is a framework that creates and shares memory between two processes. So this can happen dynamically when the server is running. Instead of solely relying on a main static shared memory that is created at the start of the server process, this DSM can help you create memory on the fly. Some of the APIs that are used in DSM. First one is DSM_create. So this allocates memory for DSM segment and initializes a descriptor. This descriptor contains the local mapping of a DSM in a process. So to establish a communication via dynamic shared memory, one of the backends, the coordinating processes, one of the processes creates DSM and maps this DSM to its local memory. The mapping of this DSM is then shared using a handle. It puts this handle somewhere in the main shared memory or in some way sends it to the other process. The other process uses this handle to attach this segment to its own address space, mapping it to its own address space using DSM_attach. Once both the processes have attached and mapped this DSM to their own address spaces, they can use DSM segment address to get the address of this DSM mapping, which is basically a local pointer to that memory to store any address, any data. Once a process is done using this DSM, it can call DSM_detach, which will detach this DSM from this process's memory. It will unmap it. And once all the processes have unmapped the DSM segment, it will get destroyed. Now let's look into dynamic shared area. So this is an abstraction on the top of a DSM. DSA is a shared memory heap which can allocate memory using DSA allocate and DSA free. So what DSM does not provide is allocation of smaller chunks, allocation of different data structures. So to allow that, we have DSA, and DSA internally attaches and detaches different DSM segments, and it acts like a heap for shared memory. It returns pointers, which a user can use to allocate different data structures. These are pseudo pointers. They are converted into backend local pointers before they are dereferenced. And pseudo pointers can be shared between other processes which want to use that memory. So these are DSA APIs. DSA_create is used to create a DSA area, and it returns a DSA area mapping. Again, it contains mappings of various DSM segments. It is local to the backend where the DSA create is called. And this backend can then, again, like DSM, use a handle, DSA get handle, can give a backend a handle to share it with the coordinating process, so that the coordinating process can also attach and share the memory using the DSA. DSA underscore pin is used to keep the DSA around even if backend exits, even if the creating backend exits. So this can be used if we don't want to go through the overhead of creating and deleting a DSA for every call, for every functionality. So this effectively retains the DSA for the lifetime of the server. So this is a useful API. So another API is DSA pin mapping. What this does is it keeps the session until keeps the DSA until the end of the session. Otherwise, if it is created in a transaction, it gets deleted at the end of the transaction. So what this will do is it will keep it at the end of the till the end of the session. Right. So I think I've already described the DSA allocate and DSA free. As you would imagine, they are used to allocate memory and free memory. So how this is used, how this is useful in designing this feature was that I could, whenever statistics are required, a DSA allocate is called to allocate memory, dump the statistics, and when the use of the statistics is over, one can call DSA free, and that memory will be given back to the DSA for reuse of future statistics dumped. Let's look at the shared memory structure. So this is how the shared memory for this particular memory context statistics monitoring feature looks like. On the left, you can see static shared memory. The static shared memory basically consists of an array of process-specific data. The index of this array is the proc number, and the number of elements in the array is the max processes. So, so this is defined statically at the start of the server. These contain values specific to a process, like LW log or a condition variable. LW log that would be used to synchronize access to the statistics. Condition variable that would be used by this process to signal all the waiting processes, all the processes that are waiting for its statistics. So, and there could be like other information like metadata for the statistics that we are sharing. Another thing that the static shared memory array contains is the DSA underscore pointer, which is a pointer, which is like a pointer returned by DSA underscore allocate. This points to the variable size chunk of memory used to report memory context statistics. Since a memory context statistics can grow, rather a memory context can grow to a really large value, we need a way to have a variable size chunk, and that's what DSA pointer gives us. So as you can see, each process, size of the dump of each process can vary, and that's handled using a dynamic shared area as shown. These variable size chunks could also contain pointer to other variable size chunks if required. So that way it can be exploited. So I'll try to describe in this slide overall flow of data in this particular function. So what you see on the left is the PostgreSQL client backend, where a monitoring function will run. So when you run a monitoring function, what will happen is the monitoring function will send a proc signal. Obviously, the proc signal will be sent to the process from where it wants the stats. And then on the right, you see that process, PostgreSQL process. It receives this signal. It sets a flag in its address space so that it knows that the signal has been received. It does not process it immediately because that can be expensive. This flag tells the backend that it needs to go back and process this interrupt whenever it's safe. So that is done by a function called check for interrupts in Postgres. So whenever a check for interrupts function is called, this signal will get processed. By processing, what it will do is it will create the statistics, it will create the area, the dynamic shared area, and it will copy the statistics to that memory. Once it is done copying, it will signal the condition variable on which the client is waiting. So once the client had sent the signal to the process, it started waiting on a condition variable. At a time, a Postgres process can wait on any given condition variable. And since we have defined process-specific condition variables as described in the shared memory diagram, a PostgreSQL client backend can wait for a specific process's condition variable. Whenever that process is finished publishing stats, it will send a signal on that condition variable, and the particular client that was waiting for those statistics will be woken up. It will wake up, read the stats, and output the latest statistics. In case a PostgreSQL process is not able to send statistics, client backend waits for a given seconds, and after those many seconds have passed, it will time out. With last published statistics, and if there were no statistics published, then it will just return null. The number of seconds that a client backend waits can be configured by the user, which we'll see in the signature of the function. So this is again about the synchronization, and what is used in this particular monitoring function is the LW logs. Since the amount of time taken to copy memory stats from one location to the other could be significant, so LW logs are a better fit as compared to, for instance, a spin log. So I've used LW logs here. Condition variables, as I described earlier, is used to signal between these processes so that they can be notified whenever a statistics dump is ready. So these two are the synchronization primitives that I've used in this function. So let's look into why dynamic versus static. So by now it must be clear to you all that dynamic memory allows the use of expandable memory, which can be used to store variable number of statistics. And this way we can have a dedicated space for each process without pre-committing large amount of memory. So that's why dynamic shared memory is a better fit here. If you imagine something like a static shared memory, it would have limitations, and if the stats that are published don't fit in that limited memory, then a process will have to wait for that memory to become available. So there would be wait times at both publishing and the client side, so that this will impact the performance. So something like a dynamic shared memory is a better fit here. So why DSM versus DSA is was also described because DSM provides a raw fixed size blocks, but it does not give you freedom to allocate smaller chunks, does not provide a heap-like interface where you can allocate and deallocate smaller chunks with different data structures. So that's why DSA is a better fit. Another design concern was, since these statistics can grow to a really large value, there has to be a limit on what we can store. So, or the excess statistics have to be handled in some way. So these excess statistics could be handled using a file, but that would involve file handling overhead and will add I/O costs. So the way it was done in the function was to summarize all these excess statistics and copy them as a single record in the shared memory. So all the rest of the statistics are provided as a cumulative total rather than having each statistics for each individual memory context. So now let's look at the SQL function API. So the name of the function is pggetProcessMemoryContexts. It takes 3 arguments. First is PID. Second is, so PID, as you can imagine, it's the PID of of the process for which you want to query the statistics. Get summary is a mode which can be used to cut down the amount of memory required for these statistics, for saving these statistics, in case what a user wants is the overall like consumption number. Then what they can go for get summary, because that will only store context statistics for at level 1 and level 2. Level 1 meaning the top memory context, and level 2 meaning all the children of the top memory context. So, but all of the further children are, their stats is reflected in the level 2 context in the form of a total. So it will, the numbers displayed there would represent all of the context, just that the individual entries won't be there. So it provides a summary of memory consumption. Timeout is the third argument. This is, as I described earlier, is used to determine how many seconds a monitoring function will wait for this latest stats to get published. If these many seconds have passed, it will go ahead and publish older statistics, or it will publish null. And the client can retry. So let's look at the output of such a function. What it will give you is the name of the context, total bytes, which means the total amount of memory that is allocated under that context. Total n blocks means the number of blocks that correspond to the total bytes. Free bytes are the bytes that are free in that context, and free chunks are the chunks that comprise the free bytes. The fifth output here, the number of aggregate contexts, tell you how many contexts, the values for how many contexts are displayed in that particular row. So num ag context equal to 1 means the stats for only the top memory contexts are displayed in that row. This will change if we display summary. If we summarize more context in a single entry and single row, then the number of aggregate contexts will reflect the number of child contexts we have aggregated for that particular output. So here the get summary was false. So we have displayed the output for every context individually. Hence the number of aggregate contexts is 1. So here the second argument, if you see to the function, is true, which is get summary is true. What it does is it displays the top memory context and all its children, and the rest of the children are all aggregated. So if you can see, cache memory context displays the value of all its children also. Like, so the memory consumption by itself and all its children is displayed in this particular output. And you can see the number of aggregate contexts represent the number of children that have been aggregated in this output. One can think of a customized output. So this is an example from PostgreSQL documentation. And this way one can get a sum total of memory consumed by a particular context. You can query the context by context name and just query the sum of the total memory consumed. So I'll quickly touch upon the API. So this was a function that was an on-demand monitoring function, on-demand stats monitoring function, which also deals with variable stats. So this was the first of its kind in Postgres. So we can think of developing an API for this, which can be used for future on-demand statistics, which would be variable stats and which would require a dynamic shared memory. So a function, so I tried to like encapsulate some of the individual steps that I had to do while doing this, writing this function into a common function that could be used by other functions, other functionalities like this. So PG dynamic report start. So this could be like so obviously this needs more thinking, but I just wanted to put it out there that some of these things can be encapsulated into a API. So what PG dynamic report start will do is whenever a Postgres server is queried for dynamic stats, any process is queried for dynamic stats, it will go ahead and create a dedicated DSA area for it. And it will create a local mapping. It will also put a handle somewhere in the shared memory. So that whenever any other future process wants to query on-demand variable statistics, it will take that handle, it will attach to it, it will map that area, and then can go ahead with publishing and reading statistics. PG dynamic initialized shared memory. So as you have seen that there were two components to the shared memory, fixed as well as variable. So PG dynamic initialized shared mem tries to describe the shared memory, the static shared memory structure. This will consist of fixed statistics, which would be the metadata about the variable statistics, logs that would be used for such kind of statistics, and the variable statistics would be represented using a DSA pointer, which would be stored in a fixed statistics. This could be the shared memory structure. A PG dynamic report end function can be used to clean up the area which was used to for this dynamic on-demand statistics. I think that's it for this talk. This is, yeah.